Good afternoon, everyone. We're into the rump part of the semester. I hope you're surviving. Made it through some midterms, almost there to Thanksgiving. Today, I want to show you about DNS, which is pretty cool. It's like all DNS all day long today. I want to show it to you just because I think it's worth knowing about this piece of how the internet works, regardless of anything to do with security. And also because it's kind of like this beautiful mechanism for like a scalable database that spans the entire world. And then also because I want to show you some of the security problems with DNS so that you can have a case study of looking at a system that was designed maybe without thinking so much about security, or when security wasn't quite the same salience. And you can see what some of the security challenges are. And then I'm going to show you how to defend against those with a system called DNSSEC, which is like a beautiful example of how you can use signatures and public key cryptography to provide data security. Okay, so let's start with DNS. We talked about TLS last time. I'm just going to take that for granted that if you want to have a secure channel, a secure communication line with another party in real time, we have a way to make that cryptographically secure. The answer is TLS. And today I'm going to talk to you about DNS. And what DNS is DNS is a lookup system so that you can enter into your computer a human readable name, and that your computer can turn that into an IP address. When we work with our computer, we'd like to be able to type some human readable name in. Like I want to go to the website CNN.com or Amazon.com. That's a human readable name. I've heard of the brands Amazon and CNN. But my computer wants to work with an IP address, because remember I said that the IP protocol involves needing to know the IP address so you can know where to send a packet. And the reason why your computer likes an IP address is because the IP address has some notion of location built into the address. When routers look at the IP address, it's not some gobbledygook numbers. Those numbers give the routers an idea about how to get a packet to that destination. So your computer wants an IP address so that packets can be routed, but you as a human want some human readable name. Domain names are the one human readable name that we use for identifying machines. So if you send email to Joe at Stanford.com, the Stanford.com is a domain name. And we need some way to translate between the two. And let me just mention that the domain name is not the whole URL, it's just the part of the URL that identifies the host, identifies the server. Okay, so what DNS is, it's a network system where if you have a domain name, you can figure out what IP address that corresponds to. It maintains a mapping from domain name to IP address. Okay, so in the DNS, you can think of it as a giant database that spans the entire world, where the entries in that database are a host name and the IP address that corresponds to that host name. Or you can think of it as a big like hash map or something like that. Okay, so when I type google.com into my browser does a DNS lookup. It looks up into this giant table to try to find the IP address that's associated with google.com, and then it opens a TCP/IP connection with packets sent to the destination address of this IP address that it got from DNS. So We want this to kind of be reliable, always work. Because if it stops working, I won't be able to like use web pages and send email. And we want it to be fast so that when I like type in a domain name into my browser, the web page loads quickly and doesn't wait 10 seconds. And the DNS is like a design to try to achieve all those goals. And DNS works by having a bunch of servers around the internet called name servers that are responsible for keeping track of all this information and figuring out how to help you do lookups. Okay, so a name server is just a server that's running, it's listening, waiting for people to contact it to do a lookup. You can contact a name server and says, I have a domain name, help me figure out the IP address, and the purpose of the server is to help you. Each name server is running on some machine, so that machine has its own domain name and IP address. So to figure out how to contact a name server, I'll like, before I can start doing this DNS stuff, I have to like figure out how to contact that name server. So like if I have an IP address of a name server, I can just send a packet to it directly. But if I only have a domain name of a name server, I have to like first look up its IP address, and then, which is another DNS query, and then I can know how to send packets to it to help me with the real DNS query that I wanted answered. So like 61A style recursion is going to get used here. Welcome to the class, just what you wanted to hear. Okay, so to look up the IP address associated with a host name, your computer sends a packet to a name server. The request contains the host name, and then you can think of the response comes back with the IP address. Actually, the response comes back with this row in the database, this mapping. The response says, for hostname www.google.com, the corresponding IP address is such and such. That's what's in a response. Now, the most naive design would be we would have one name server that would keep track of all this information for everyone. Everyone would contact that name server to do a lookup. Everything would be simple. And the problem is that doesn't work. It doesn't work because there's too many, every machine is making DNS lookups all the time. Every time you visit a new web page on some website you've never been to before, your machine's going to make a DNS lookup. So this one server will get totally overloaded with requests if we only had one name server servicing everyone. So we're going to have to split this up amongst multiple name servers so that we can handle all the load. Can anyone give me another reason why it might be bad to have one name server that handles everything? Yeah? Single point of failure, totally. Reliability. If that one server fails, everybody in the world is toast. Also security, that server becomes really critical. Yeah, totally. So the DNS is going to try to be designed so that we can have multiple name servers for all these reasons. One, so we can split up the load. Another, so we have reliability. So if one of them can't answer, there's others I can ask. And then, well, it wasn't really designed so much with security in mind. So we'll get to that later in lecture. But the tricky thing is, if we have multiple name servers, how do we split up all this data between them? One strategy could be that every name server has a copy of the full database, has all the data. 1,000 name servers, they all have the same data. Each one knows all domain names and IP addresses. Any downsides you could see with that?
Is the data?
Go ahead.
Is the data? Different place where it varies. If it's stored at each place, then it's going to take a lot of space to do that.
Yeah, so I'm trying to like start by exploring what the options are here. I'm not telling you how it actually works just yet. I'm like imagining you're a designer of DNS and you're like thinking through what the options are and what the trade-offs might be. So let's start with the simplest design. A copy of the data is stored at every name server. There's 1,000 name servers.
like, if you were to like partition, all of the names into different servers, then that might be slower because.
Okay, hold on. You got a better design already. Whoa. Slow down. I got to come back to you with your better design. Okay, so one problem with storing a copy of the data on every server is, and I love it. I'm sorry, I'm just going step by step. I'm slowing us down a little. If we store the same data on all the name servers, space, that's a lot of data. Any other downsides? Yeah? Hard to keep them synchronized. Why do you need to keep synchronized?
Like Google changes that IP address, like we all need to be doing this.
Yes, if Google changes the IP address for one machine, they have to let all the name servers know. And then they all have to have that update. So these name servers are going to be getting every update has to go to all 1,000 of them. So synchronization might be really painful. Okay, good. Yeah. So another design, your other design. Partition all the names. So we have 1,000 name servers and each one has 0.1% of the names. Great. Then we would not have any, the synchronization problems would be solved because when Google updates an IP address, they only have to contact one name server to say update your data. We wouldn't use as much space. Any downsides you can imagine with that?
Everybody uses Google, right? So it's going to be the same problem as if you have one big server, right? It's like everybody's going to go to the same.
Oh, everybody goes to Google so that whatever name server has the IP address for www.google.com might get hammered really hard. So this might not be ideal from a load balancing perspective. Another problem?
Maybe you should take care of the density, like which websites are most frequently like correspondingly established servers that.
Oh, clever. So not each server has 0.1% of the names, but like 0.1% of the load. Okay. Any other problems you can envision with this design? We were worried before about space and reliability and security. I guess let's not worry about security for the moment, because we're not going to get to the security part. We said this takes care of space. How is it on reliability? It's bad. It's bad. If that one server stores the IP address for www.google.com and that server goes down, there's no other alternate I can contact. So many copies of the data is good for reliability, but bad for synchronization. One copy of the data partitioned up is avoids synchronization problems, but is bad for reliability. And also we'd have to figure out how to partition up the data. And by the way, I like your idea you're thinking about try to partition them by load, but then a challenge we'll face that we'll have to solve somehow is when my machine wants to look up a domain name, we would have to know which of the 1,000 servers to go to, which might be a little tricky. Okay, so those are some of the challenges in the design space that it's not entirely clear how to resolve. Maybe we want to do some partitioning, but maybe we want some redundancy. We have to make sure that clients can figure out which name server to contact to get the data they want. If there's multiple copies of the data, we might have to deal with synchronization. How are we going to juggle all this? So this is one particular design that attempts to try to find some like reasonable trade-off against all of these considerations. Okay, so the first idea in the real DNS, not every name server has all the data. So one name server will have information about some of the host names, but not others. So clients need a way to know which name server to contact to get the answer to their lookup. So the first idea is if a name server doesn't know how to answer the query, we'll make sure that there's a way it can figure out some other name server that can help you. So it's like the clerk at the department store who's like, sorry, I don't know, but go to the 3rd floor and I think someone there can help you. And then the clerk, you go up to the 3rd floor and they're like, oh, I don't know either, but if you go to that department on the north side of the 3rd floor, I think they'll help you. So Name servers might not know the answer, might not have information about the host name you're looking up, but they can direct you to one that will, or they can help you get the information you need. And the second idea is that to partition the data amongst the name servers, the DNS uses a tree data structure, uses a tree hierarchy. And the idea is you're going to start at the root of the tree, and the information you want will be at one of the leaves of the tree, and the root will help you find a path to get down to the leaf node, the name server that has the data you're looking for. Okay, so here's how the tree structure works. The tree structure reflects the dots in the domain name. Like everything that ends with .edu is supposed to be like for educational organizations, and .com is supposed to be for commercial organizations, and .org is supposed to be for nonprofits. So we're going to have a root of the tree, and then beneath the root, we're going to have one node in this tree for each of these top level domains like .com or .org. And then beneath each of that is names that end with that top level domain. Like under .edu will be berkeley.edu and mit.edu. And then if you have a domain name that has 3 components, like cs.berkeley.edu, that would be a child of berkeley.edu. And if you had www.cs.berkeley.edu, that would be a child of cs.berkeley.edu. So you get a tree structure like this, which hopefully also reflects some of the administrative, like organizational structure or boundaries. Like probably there should be someone at Berkeley who can like know how to find out IP addresses for all the host names that end with berkeley.edu. Because Berkeley is one organization. And MIT is another organization. So it makes sense to like have some entity be responsible for all the names that end with mit.edu. So if you want to look up the IP address for www.cs.berkeley.edu, you start at the root of the tree. And the root of the tree says, I don't know the answer. I don't have that information, but it sounds like you're asking about a .edu top level domain. So let me direct you to the name server that is responsible for .edu domains. So then I will contact the .edu name server. And the .edu name server will say, I don't know, but it sounds like you're asking for something that ends with berkeley.edu. So why don't you contact the Berkeley name server? I can tell you how to contact the Berkeley name server. So the .edu name server doesn't have to know about all names that end with .edu. It just has to know how to contact the berkeley.edu name server and the mit.edu. There's one name server for each node in this tree, and a name server at any point in this tree, at any node in this tree, has to know how to contact the name servers for all of its children.
Like if the .edu
Yeah.
fails.
Uh-huh. Yeah. So far, the way I'm describing this has no reliability because there's no redundancy. If the .edu name server fails, all my lookups for any .edu domain name are going to fail. Yeah. Totally. So we're going to have to add reliability. How could a name server fail? Needs a software update, so we have to reboot it and stops answering for a couple of minutes. Someone took a backhoe to their internet connection. Data center somewhere. Yeah. Someone took a sledgehammer to the computer. Someone was the janitor was cleaning the floor and they needed to plug in their vacuum, so they unplugged a plug and they plugged in their vacuum. I don't know, any number of things could cause. Okay. I've heard we were the first .edu to be. Okay, so as I said, each node in this tree, each box here is a name server. And the label here represents what queries the name server has to know the answer to, is responsible for answering. So the name server, the .edu name server is responsible for telling you, helping you get the answer to queries about any domain name that ends with .edu. It might not directly know the answer, but it can tell you where to go. But if you ask the .edu name server about mail.google.com, it'll be like, oh, not my problem, not my responsibility. I can't help you. You're not supposed to start with me. You're supposed to start with the root. Okay. For each node, there's a name server, and that name server has a local database of a bunch of domain names and their IP addresses. Also, there can be delegation, which means you have a child with a name server. So for instance, berkeley.edu name server knows the IP address for www.berkeley.edu and calcentral.berkeley.edu. It doesn't know the IP address for www.eeks.berkeley.edu, but what it does know is the IP address of the name server, of a name server that is responsible for eeks.berkeley.edu. Okay, so each domain name fits into one of these zones and has one authoritative name server that is responsible for knowing the IP address for that domain name. So here's how a DNS lookup works. When you want to make a DNS lookup for, let's say, eeks.berkeley.edu, you start by contacting the root name server. That's always how you start. You ask root name server, I'd like to know the IP address of eeks.berkeley.edu. And the root name server says, not in my zone. I don't have that information. But I can direct you to a name server that will get you closer to having an answer. That might have the answer. So the root name server responds and says, I don't know, but all names that end with .edu, I've delegated that responsibility to the following name server. And it gives you host name and IP address of the name server for .edu. So next, your computer tries again, asks the same question, sends the same request, but now sends it to the name server for .edu. What's the IP address of eeks.berkeley.edu? And again, the answer is, I don't know. It says, I've delegated authority for all names that end with berkeley.edu to the following name server, and gives you an IP address to that name server. So try asking there. So your computer doesn't give up. It tries again, the same question, the same request, now sent to the berkeley.edu name server. And this time, the name eeks.berkeley.edu is in that zone. So it knows the answer, and it responds with the answer. The IP address for eeks.berkeley.edu is 23.185.0.1. Do they have a? They have a cache. You can think each name server has it's like a file or a database with a listing of, here's the name, here's the IP address, here's the name, here's the IP address, or here's the name and here's the delegation. I delegate to the following name server.
Server determine which one is the closest.
Aha. It does by looking up the host name that was sent to it. So when you send this query to the root doesn't know, but it separates it by dots, and it looks at the last part Is there some path compression that goes on? Yeah, absolutely. So if we always went through this, conceptually, you could imagine it always going through this process. But if we did that, what would be the downside? What would be the downside of always going through this process? Yeah? Sorry, I just couldn't hear you.
All the traffic is still going.
All the traffic, every single request has to involve the root. So we were trying to be scalable and split up the work. So we didn't have one server that has to be able to answer all requests, but we ended up with one server that has to answer all requests, the root. So as bad, the scalability is bad right now. Good, you're trying to solve the problem. Okay, so we didn't actually, this is actually inefficient if we did this. Okay, one idea for trying to solve this. Maybe there could be multiple roots. They have just replicated, they have the same data. And in fact, there's like 13 root name servers. And you can contact any of them. They all have the same information and will all answer you. So let's split up some of the queries and give some like redundancy, fallback. But still involves sending a lot of queries to the root name server. So the other idea, the other way that we make this more efficient is exactly what you said before, caching. This system is designed so that if you've got an answer to a question, you don't have to ask it again. You can remember the answer to the question. And if you want to ask the same question, you remember you already have the answer. For instance, let's suppose that you very frequently visit the webpage eeks.berkeley.edu. The first time you visit the webpage, your computer can go through this whole process, get the IP address, and save this information in a temporary file somewhere, the cache. And then if 10 minutes from now you want to go to that webpage again, you don't need to go through this whole process again. You've got this information saved locally in your cache, in that temporary file. So that reduces the number of queries that your computer needs to make. It only needs to make a query for a new website that it hasn't like asked the IP address of recently.
I feel like how do we know like if they decide to change?
Is there an expiration? So anytime you have caching, then the next question becomes, what about like cache invalidation? What if the data changes? How do I get updated? And the answer is in the DNS, every record, this would be like a DNS record. The IP address of eeks.berkeley.edu is 23.185.0.1. Every record in the DNS has an expiration date in there. It has a time to live. It says, this is the information and go ahead and cache it for up to 1 hour or up to 1 day. So your computer will save that locally for as long as it's told it can save it. A typical amount might be a day. Your cache in your computer is large enough to store all of that. You don't visit that many websites, send email to that many domains. If you visited 10,000 different websites today, that would be like 10,000 entries. That's nothing. So it's no problem. Okay, so your computer caches this information, which reduces the number of queries to the root name server. And then there's another trick that further improves efficiency. The next trick is called recursive resolvers. And to help further improve efficiency, Berkeley will provide a server that will do lookups for you, do DNS lookups for you, and cache them. That's called a recursive resolver. The code that does all these lookups is called a resolver. So in this picture, your computer is the resolver. It's got some code on your computer that's sending all these queries. If it's running on your computer, we usually call it a stub resolver. To improve efficiency, Berkeley also has a server somewhere running a resolver. We call that a recursive resolver. And so a more efficient way that your computer can look up a DNS name is not do the lookup itself, contact the recursive resolver and have the recursive resolver do all that. Okay? So your machine wants to look up eeks.berkeley.edu. It sends that query to the recursive resolver, and then the recursive resolver does the procedure we just mentioned. Send that to the root. The root will redirect, will provide a delegation to the .edu name server. Recursive resolver will then contact the .edu name server. The .edu name server will provide a delegation to the Berkeley.edu name server. Recursive resolver will send a request for eeks Berkeley.edu to this name server, and it will get back a response. And then the recursive resolver now has the IP address corresponding to that host name, and it will do two things. It will return the final answer to your computer, to the stub resolver on your computer, and it will cache it. It will store a copy locally in some temporary file on the recursive resolver. Why is this an efficiency improvement? Yeah?
Like things. Ideally, so like you could have caches that instead we don't have caches like L1, L2, L5.
The recursive resolver can cache more things. Help me out more with that. Is it because the recursive resolver can have a really big disk that can store a lot of cached entries?
Asking the same thing over and over.
If there's multiple stubs asking the same question, you only have to go through that process for one of them. Your computer is looking up www.google.com. My computer is looking up www.google.com. When your computer does the lookup, the recursive resolver does this whole back and forth. Caches the answer. Then when my computer looks up www.google.com, the recursive resolver already has the answer cached. It doesn't need to go through the back and forth. So if you had a cache on your computer and I had a cache on my computer, we would both have to go through the process once. But with a recursive resolver, it's a shared cache. So I can benefit if anyone else in Berkeley has visited that web page today. I can benefit from the cached IP address that the recursive resolver has stored from when that other person went to that web page. So it speeds up DNS for like everyone on campus. I don't know, a lot. And it reduces the network traffic. So like Berkeley's very happy to do this because it reduces the amount of network traffic that has to go across our internet connection. Yeah. Uh-huh.
Like if we have like a VPN that's that like
Okay, how do we authenticate the recursive resolver? And if we use a VPN, what happens? I'm going to back up and ask an even more basic question. How does my computer figure out who to contact, who the recursive resolver is? My computer has a list in the configuration for this Wi-Fi network of what recursive resolver to contact. How does it get that? Does anyone want to form a guess? There's no way you would know, but maybe you can guess.
It doesn't APR that stuff.
NAT stuff. It's not connected to NAT, but it is a network configuration. Yeah. It's part of the DHCP. DHCP provides a network configuration information. It gives you things like, here's the IP address of your access point, and also here's the IP address of a recursive resolver you can use. Okay. So back to your question, how do we authenticate the recursive resolver you wanted to know, and what happens with a VPN? So far, there's no security, no authentication, no nothing. There's no cryptography, so there is no authentication. It's just IP addresses. You contact that IP address, you believe whatever response you get in the basic DNS. And with a VPN, if you connect to a VPN, connecting to a VPN is like connecting to another network. So that network might provide different configuration information. Your VPN provider might say, I've got different information for you. Here's the IP address of our recursive resolver, of the VPN's recursive resolver. You don't have to use that recursive resolver, but usually it's in your interest to, so computers are set up by default to use that. Yeah. And then, yes, I love it. Yes, totally. Also, intermediate responses are cached. Every response is a record that states a fact. And these records can be cached because they're facts. So like the response labeled 3 here is a response that from the root name server that says the name server that has authority over .edu is 3.4.5.6. That statement is also a DNS record and can also be cached. Okay? So if this morning I got up and I went to some web page on mit.edu and it did this whole lookup, and then a little later you woke up and you went to a web page stanford.edu, and we were both using the same recursive resolver, then you wouldn't have to do step 2 and 3 because the recursive resolver would have cached what the authoritative name server for .edu is.
Like, as in, this address is only valid for a day or 4 hours or something like that. So it's only cached for X amount of time.
That's right. Every record in DNS, each one of these facts comes with a, here's how long you can cache it for.
So that if you load something, then I load very soon after that, I can use your cache values.
Yeah.
If you load something like a week later, I do it.
You look it up again. If it was a week later, probably that's no longer, the caching timeout has expired. Yeah, yeah. So it's beautiful. It's like this beautiful design where everything you want to know is broken down into a set of facts. Every fact can be cached. And so that enables like this huge performance speedups. If you've already got the information cached, you don't need to look up again. You can cache it on recursive resolvers and shared caches so that multiple people benefit from the caching. And so, for instance, if the root name server goes down, but the information is cached in the recursive resolver, everybody's still able to get answers to their DNS queries because they don't have to contact the root name server. So it's an additional form of, it's not just efficiency, but also some kind of reliability benefit. Yeah.
So the response is powerful. Like if you're switching a bunch of different
No, it doesn't. It doesn't. I think the response from the recursive resolver is just the final answer. Says the IP address for eeks.berkeley.edu is such and such. But I'm not sure about that. I could be wrong. It's a good question. I shouldn't say that for sure because I'm not sure. Okay, this is the first idea I wanted you to see. How you could build a large distributed database by like expressing everything you want as a bunch of simple statements that are all cacheable. And then you have some infrastructure to cache them and figure out which server has the facts you need to know. Let's take a break, and then we'll start to keep going and look a little bit more details of DNS and the security implications. So let's take a 2-minute stretch break. I don't know. Okay, let's continue. Okay, so DNS, all these questions, these queries, and the responses, they're sent in DNS packets, which is sent over UDP. So no like TCP, like session setup, no three-way handshake, no reliability and ACKs and so on, to try to make DNS fast. Because whenever you go to a website for the first time, first you have to do a DNS lookup. We want that to be super fast. We don't want to have to do three-way handshake for every single name server we contact. That's the idea anyway. Why is it okay to not have any acknowledgements? What if one of these packets gets dropped, like a DNS query or a DNS response? It's not bad. It sounds kind of bad. What do you think? Just ask again, retry. You can always, these are like, this is an idempotent operation, asking a question. It does no harm to ask the same question twice. It's not like asking the same question twice causes twice as much money to be deducted from my bank account or something. So if I ask and I don't get an answer, I just ask again. Spoofing, okay, there's going to be all sorts of security problems. Yeah. Yes? Man in the middle, oh my gosh, it's going to be bad. It's going to be bad if there's a man in the middle. This is not designed with security. Yeah. So let me tell you about the format of these data packets. You mostly don't need to know, but it'll be useful to know a little bit, which is like any IP packet, there's an IP source and a destination address in there. Like any UDP packet, there's a source port and a destination port. The destination port is usually hard-coded at 53. That is a number that is reserved for DNS servers. DNS servers will listen for packets with port 53. The client can choose any source port at once. The resolver can choose any source port at once. Might be chosen randomly. And then in the DNS get, there is an ID number. Each query, each lookup has an ID number. And then the response will use the same ID number, so you can match up responses to the queries. Okay, so the resolver, the client, will pick an ID number, 16-bit number. Maybe it's an incrementing number, a counter, maybe it's random, who knows. And then when the name server responds, it'll use the same ID. And then the payload might contain some question records. A question record is like, I'm looking for the IP address associated with eeks.berkeley.edu, or it might have some answer records. It might be like, the IP address for eeks.berkeley.edu is 1.2.3.4. And there's actually two other sections. The authority section is if you don't have the answer about what the IP address is, but you want to point to a name server, the authority can be used to indicate which name server is responsible for, has authority over a particular zone. And additional records, when you ask a question to a name server, sometimes it might give you both an answer and some extra information that might be helpful. Or it might not give you an answer, it might delegate to a name server. So there might be something in the authority record that says the name server that can answer that kind of question is such and such. And then it might give you some additional records so that it will be helpful. I suspect you're going to want to know this too. Like, I'm guessing this might be a question you're about to have, so let me just give you the answer that I suspect you're about to ask. And it's kind of a little technical detail why that's needed. So a record is a name value pair and a type. Three things: domain name, type of record, and value. And probably the most important one is A records. A stands for, I don't know, answer or address or something like that. And that has a domain name and an IPv4 address. There's also NS records, and those are for identifying what name server is responsible as authoritative for a particular zone. And the value of a NS record is, it identifies a name server. It's actually a host name of the name server that is responsible.
That we have NS type records, because they need to.
Yep. They have an NS, every other node has an NS. Actually, every node in that tree has an NS type record. Let me back up to a picture. We're going to go way back. Responses 3 and 5 will be NS records. The response 3 will be an NS record that says .edu, NS, and then some identifier for the .edu name server. Response 5 will be an NS record, berkeley.edu, NS, and then whatever the corresponding name servers. Response 7 will be an A record, will be an IP address. And then each record also has this time to live that tells everybody how long it can be cached. This is a suggestion. The reason this is there is that it might typically be a day. Go ahead and cache this information for a day. But if I'm a system administrator and I know that I'm about to do some maintenance on a machine that might change its IP address, then I might lower the cache period down to an hour or to 5 minutes or something like that in advance, like a day in advance. Start sending out records with a very short time period for the cache, so that then when I change the IP address, everybody will get the new information fairly quickly. They won't have to wait a day to get the new information. We already talked about the sections. Authority contains these delegation, referral to a name server, and then the additional section. These are also sometimes called glue records. And I'll tell you why they're there. It's a technical detail. If I get a referral to the name server for the berkeley.edu zone, that referral will say the name server for berkeley.edu is, and give the host name of the name server. The host name. To contact that name server, I need to know the IP address, but I only get a host name. So I'm going to have to do another DNS lookup to find out what the IP address is that corresponds to the host name for the Berkeley name server. To spare the resolver from having to do a whole nother of this process that's recursive, maybe getting into some infinite loops, I don't know what, it provides an additional record, a glue record, that says, I know you're going to want to know what the IP address for this host is, so let me just tell it to you in advance. So maybe the authority section says the name server for berkeley.edu is ns1.berkeley.edu. And then there would typically be a record in the additional section that says the IP address of ns1.berkeley.edu is 8.9.10.11. So that you don't have to do a whole nother set of queries just to find that information. Okay. And then resolvers cache everything. Basically, all the records they receive, they cache. First order approximation, anything you get, cache it. The more you can cache, the better. You can look at this yourself. You can see this happening by running the dig command on a Unix machine, like log into one of the Hive machines and run dig. You have to set this command line option no recurse, so it doesn't use a recursive resolver. It does the whole thing itself. And you provide the name that you want to look up, and you provide the IP address of the root name server. Those are hard coded. I don't think they've changed in like decades. And if you run that, you'll get a response. And it's like, oh my gosh, all this stuff. But it's actually not too hard to interpret the response that you get back. This is the response from the root name server. And there's some DNS header stuff that like, whatever. Yeah, there's an ID, whatever. Not that important. And then this is the data payload. This is the part we really care about. And you'll see that the response included the question that was asked. The question was, eeks.berkeley.edu, what is its address? And there's no address listed because there's a question. We don't know what the address is. We're hoping it'll fill in the address. So that's the question. It like reminded us, here was the question you asked. And then there's a count here saying how many do we have in the answer section? How many records in the authority section? How many in the additional section? The answer section has 0 records. So the root name server did not answer our question. Instead, it gave us a referral. And the referral is to another name server. And it did that by providing us with this NS record that says, I can tell you a name server that is authoritative for the .edu domain. Go ask them. And in this case, it actually gave you 3 such name servers. You can ask any of them. This is a reliability redundancy measure. If one of them is not reachable, go ask a different one. So the authority section has the name servers that are responsible for .edu. And then you can see down here in the additional section, it helpfully said, I bet you're going to need to know what the IP address is for those names. So let me just tell you proactively what the information you're going to need to know to make use of that. So it contains an A record with an IP, with the address. Yeah. What is the IN? I don't know what the IN is.
You don't even need it. So-
Yeah, I don't know why it's there. I don't know. Someone look it up and tell us. I'm sure Google knows the answer. ChatGPT knows the answer. Or it'll give you a plausible sounding answer, one of those two.
Flat, always IN from internet, except for special queries to use to get information about DNS itself.
Oh, I see. IN is for internet. Okay, there you go. Thank you. Thank you, textbook. Okay, so what do we do next if we're doing a recursive query? We found out that we need to contact the name server at this IP address. So we're doing this all manually. We need to do the same command, but now with the IP address for .edu name server. So I plugged in that IP address we got from the referral. And here you get an answer. And once again, you don't get an answer, you get a referral. This response says, I can tell you the name servers that are authoritative for berkeley.edu and their IP addresses, and here's the IP address of one of them. It doesn't have to be. This is telling you 3 options. You can use any option you want. You could always pick the top one. You could pick one randomly. You could try. But the point is, there's multiple options. So if you contact one and you can't reach it, you can retry by contacting a different one. Okay, so we do it again. Now contacting the name server we were pointed to. And this time we get an answer. This time we get the IP address for eeks.berkeley.edu. That was the information we truly actually wanted. And we now know the IP address that can be used to send a packet to eeks.berkeley.edu. Do all the name servers have the same information?
It's like,
Yeah, you can contact any of them and they should give you the same answer. Hopefully. Assuming nothing has gone wrong. Yeah.
this.
Where did this IP come from? This IP came from, we contacted Berkeley's name server. We found out that the IP address for a name server that is authoritative for berkeley.edu. So it has to know the answer to all queries about names that end in berkeley.edu.
Oh, it's, yeah, the additional section. One of the, name servers that you could access. And because it's not recursive, we just net it. Next to it.
Yeah, I'm simulating this recursive procedure here manually, one step at a time. Okay, so that's how you could you could try it yourself and see with dig. And you can see there's like cache period. So this one's 24 hours. So security, it's a security class. I guess I'm contractually obligated to say something about security. So let's say something about security. What are the security risks in this? Well, there's no security. That's a risk. One problem is if there's a man in the middle can send a fake response. And the resolver, your computer will believe it. Because there's no authentication or encryption or anything here. And it's even worse than that. It's not just that your computer will believe it, or just that the resolver will believe it, but because there's all this caching, the resolver will cache the information and continue to believe it. So one attack on very early DNS systems was that I set up my own name server for davewagner.com. And I wait for someone to look up like www.davewagner.com. And I respond with an IP address for davewagner.com. But I also respond with this additional record in the additional section that says, by the way, also, the IP address for Amazon.com is, and then I give my own IP address. And in the very early days that actually worked, whoever was doing the lookup would receive that response and cache that. Say, ooh, good, extra helpful information. I'll add that to my cache. And then if they didn't already have an IP address for Amazon, now they have an address for Amazon.com. And then if they, in their browser, go to Amazon.com, their computer is using the cached IP address that I provided. And so they're actually contacting me, not the real Amazon. And I am now a man in the middle. And if there's no HTTPS, then I might be able to attack them. How do we fix that? That problem had a fairly easy fix. We didn't need any cryptography. How could you fix that problem? Yeah? Have
DNS servers that everyone knows where they are.
dedicated DNS servers and only use the dedicated ones.
Yeah.
Yeah.
It doesn't scale well.
Yeah. Basically get rid of this whole distributed system and use some dedicated, trusted, centralized ones.
So get rid of it, but at least in the early days, you could probably maintain some of this.
Yeah. Is there any way we could defend against this while still maintaining this kind of a distributed structure? Awesome. Yes. Okay. You should be a DNS engineer. I mean, the dumbest, crudest thing is don't trust additional information. The additional information got us in trouble. But you can have a more systematic defense, which is don't trust additional information about domains that this name server is not authoritative for. When you got referred to my name server, that referral said my name server is authoritative for davewagner.com. That means that my name server should be allowed to give you answers about host names that end in davewagner.com. You should be prepared to believe it, but don't believe my name server if it tries to make claims about IP addresses for any other domain names. Okay, so that problem was easily fixed. For each name server, we keep track of which zone it's authoritative for and only accept responses, filter out any responses it's not authoritative for. But it does mean if there's a man in the middle and a man in the middle responds with a fake response, then that will get cached by the recursive resolver, and everyone who's using that recursive resolver now gets bad information. So that's called cache poisoning. So in some sense, this caching is great for performance, but it like exacerbates the security problems. An attacker who can do a man-in-the-middle attack on one DNS lookup can poison the cache of a recursive resolver and affect all Berkeley affiliates. Okay, so cache poisoning is one risk. Malicious name servers are another risk. I already just talked to you about that. We already talked about how to defend against malicious name servers. The defense was only accepting responses that the name server is authoritative for. There's a fancy name for that. It's called bailiwick checking. I don't know why it got called that, but that's what it got called. Yep.
Say like your own website offers like a mapping from google.com, but you just like ignore the google.com.
Yep.
Like, you actually like that is the whole, like your domain.
Just ignore whatever my name server is not authoritative for.
He like say this one is malicious and like machine.
You could imagine a strategy where if the resolver detects that a name server is responding with records that it's not authoritative for, then like blacklist that server. That could be an alternative strategy. I don't think it is. Either would be fine. Yeah. And then another security risk is, well, we just talked about this, man-in-the-middle attacks. So a man-in-the-middle attacker can send spoofed responses and poison the cache. So a consequence is that DNS is not secure against on-path attackers. If there's an on-path attacker when I am doing a DNS query, the on-path attacker can observe my query and then send back a spoofed response. Spoofed response means the attacker sends it, but puts in the source address, the name server's IP address, to make it look like it came from the authoritative name server, even though it actually came from the attacker. And if the attacker's spoofed response comes back to my machine before the legitimate response does, then I'll accept the spoofed response. And moreover, the resolver that's receiving this response will cache it. So it'll continue to cause harm. The response has to have the right ID field to be accepted, but an on-path attacker can eavesdrop on all of the requests and see the ID field that's in the request and see the port number and see all the information in the request and then copy over that same ID into the spoofed response. So an on-path attacker has all the information needed to send a spoofed response that will be accepted by the resolver. So DNS is in some sense fundamentally insecure, at least against on-path attackers.
Just obvious like defending it all with the like, because I feel like if you're an attacker, you want to be like as large as possible.
The attacker could copy the time to live, or could provide a time to live that's like a year long. Keep this bad information forever. I don't know if there's an upper limit. Yeah. So it's bad. But the reason why people for a time thought maybe it's not that bad is because it's vulnerable to on-path attackers only, but not to off-path attackers. Because off-path attackers won't see the source port, they won't see the ID number, So they won't know how to fill in all the fields in a response, a spoofed response. And so an off-path attacker can't mount this attack. So most people in the rest of the world can't attack me. Someone compromises a router along the path that my DNS request is taking, they can hack me. But a random person in Bolivia can't attack me. That was the kind of the comfort, the reason why for a long time we thought, I know at some level it's not secure, but maybe it's good enough that I don't need to worry about things too much. I am like walking you through a chronology of our increasing understanding of the security risks facing DNS. So I have to tell you one more discovery that happened 20 or 30 years ago, maybe 20 years ago. So let me do that first before I tell you what's true today. So for off-path attackers, the off-path attacker has to get the right ID number in the response. Otherwise, it'll be ignored. And if the ID number is randomly generated by the resolver, then the off-path attacker has to guess that 16-bit number, and they have a 1 in 2 to the 16 chance of getting it right. Which means that an off-path attacker who's willing to keep trying 65,000 times might get it right once. So it's just barely feasible for an off-path attacker to try and send a lot of spoofed responses. They'd have to know the right time to send the spoofed response. They'd have a 1 in 2 to the 16 chance of getting it right each time. It's kind of uncomfortably on the borderline of what might be like realistically feasible for an attacker to do. What if the ID number was incrementing? In some early implementations, the resolver chose ID numbers that were incrementing by 1 each time. Each new query it sent out, it incremented the ID number compared to the previous one. Still a 16-bit value. Would that change anything, or is it about the same? It's kind of hard to tell. Yeah? What's that? Kind of depends on the initial value. Okay, what if the initial value was 0? So then maybe when a computer just boots up, the first query will have 0. So maybe we could like somehow, the attacker could try sending spoofed responses with 0, hoping this is the first one after boot and hoping they have a somewhat increased odds of success. They somehow knew that you were rebooting right now, maybe they'd have an increased chance of success. Maybe if they had some way they could like crash your computer, but couldn't get malware on it, could just cause it to crash and reboot, then they could start sending spoofed responses with an ID field of 0. Maybe attacks could be possible. So let's suppose the initial ID number was random, but it increments by 1 for each query. Then the attacker just has to guess. Kind of a trick question. If the ID field increments by 1, it actually enables an attack. Suppose the attacker is trying to attack me, and they get me to visit their website. And then somehow they know that I'm going to go to Amazon.com next. Can you think of any way that could help them? What's that?
If they correctly guess the ID number for after the website, then they would know the ID number.
If they correctly guess the ID number when my computer looks up their website, they'll know the ID number for Amazon. But guessing that sounds like guessing a 16-bit number, so it seems like back where we started, doesn't seem like that helps. Who controls the name server for their website? They do. Could that help them any? Yeah? Yeah. When I go to the attacker's website, evil.com, my computer will do a DNS lookup for evil.com. They might have configured a name server for evil.com. So my DNS lookup for evil.com will go to their DNS server and they can observe the ID field that my computer is using. And then if next I go to Amazon, my computer will make a DNS lookup for Amazon.com and they can guess that the ID field for that lookup will be 1 higher than the lookup for evil.com. Or maybe 2 or 3 higher, it could be. So they could send spoofed responses for an Amazon lookup with an ID field that's 1 or 2 or 3 higher than the lookup I did to their DNS server for evil.com. Does that make sense? How could they predict that I'm going to go to Amazon next and predict the timing? Oh, did you have a question?
Put a website that's like close to it. Like, so you accidentally redirect, you might mistype it. You go to their website and you go to the
Aha, it might be not evil.com, it might be amzon.com. And if I mistype Amazon as Amazon, then I go to the attacker's website and they figure that next I'm going to go to the real Amazon when I realize it's not them. Uh-huh.
Maybe if they're search things up, maybe.
They can do even more. If I go to their website, they could put a link to Amazon and hope that I click it. Oh, they can even do even more than a link and then hope that I click it. What else can they do? Of a button that they hope that I click.
This is a nice link.
Oh, this is an awesome link to see great cat pictures. You totally want to click here. Put an iframe that loads Amazon. Totally. Or, yeah? Yeah.
I'm sure Amazon.com and Amazon.com definitely the same. But then you just your escape and log in.
Okay, you're describing a phishing attack. I don't want to go through a phishing attack. But yes, the attacker could create their website, evil.com, and on the evil.com website, they could have an iframe for Amazon that displays Amazon. Or they could have a redirect that causes your browser to automatically go to Amazon next. So they don't even have to do much prediction to know that my browser is going to go to Amazon next. They're forcing my browser to go to Amazon next. It's guaranteed to happen almost immediately. So they know exactly the timing. They know exactly the ID number to use. So if the ID number incremented and some early implementations incremented, actually an attacker can spoof responses with really high reliability. Does that make sense? So it's critical that the ID number be random. And if it's random, then the attacker has to guess. 1 in 65,000 chance of guessing correctly. They can still do this attack, but they have to guess randomly now. And 1 in 65,000 chance of success. If they could try 65,000 times, they'd probably succeed once. Okay. So ID numbers have to be random. They better be random, or there's really bad attacks.
They can like direct you to like Amazon.com, like why wouldn't they just direct?
Because in a world, let's suppose that, okay, these attacks were conceived before TLS, before HTTPS was widely deployed. when my browser goes to Amazon.com, it sends my session cookies, right? So if the attacker can make my computer think that the IP address for Amazon.com is the attacker's machine, my browser sends a request when I load Amazon.com to the attacker's machine, a GET request that contains my session cookie. And my session cookie is everything that's needed for the attacker to log in as me and make purchases as me on Amazon. Does that make sense? They steal my session cookie, they have access to my account. That's not a threat anymore because now Amazon uses HTTPS, and so it doesn't work. But it used to work. So it used to be really bad if someone could get false information in the DNS.
Nowadays, like visit a website directly without any sort of introduction. Like, is there nowadays any danger in clicking link apart from like leaking activity?
Your browser is supposed to make it safe so you can click a link anywhere, go to any website, and there'll be no harm done. Unless you like deliberately reveal information to that website. Yeah, so if there's no browser vulnerabilities or bugs, it's supposed to be safe. There always could be some, buffer overrun or use after free or some format string vulnerability in your browser somewhere that makes it not safe. And if we discover those, we try to patch those as quickly as possible. Hopefully those are rare. Yeah, and the same origin policy in your browser tries to make sure that if I go to some random website, it's safe, it can't harm any of the data that or like passwords or anything that I have, abilities that I have on other websites. So it's supposed to be safe. Okay, ID numbers need to be random. For a while, we thought as long as you make ID numbers random, you're probably okay. And then Dan Kaminsky came along and found a serious attack. What he found was that an attacker doesn't need to make 65,000 tries to succeed in sending a spoofed packet, that it's enough to try a few hundred times. It's a really clever idea. It's a variant on the kind of attack I was talking about before. So the attacker sets up their own website, somehow gets me, the victim, to go visit that website. And then they put some stuff on the website, like iframes or image tags, to get my browser, the victim's browser, to load stuff from other domain names, to do DNS lookups on those domain names. So the attacker knows that there's going to be a DNS query made at exactly that time. The attacker tries to send a spoofed response. The difference is, his trick is he gets my computer to make a whole bunch of DNS lookups. And he arranges sending a spoofed response so that if their spoofed response is accepted as a valid response to any of those DNS lookups, he wins. So on the attacker's website, the attacker includes like 4 images, let's say. Each image loaded from a different domain. My browser will make 4 DNS requests to look up the IP addresses for those 4 names. The attacker sends back a spoofed response with a guess at the ID field. And some lie, some malicious response in the additional information field. And the thing is, those 4 DNS requests will have 4 different IDs. If any of those 4 IDs match the ID in the spoofed response that the attacker sends, the spoofed response will be accepted. So now the attacker gets 4 out of 65,000 chances of success. Doesn't sound like a big improvement, but actually you can get a big improvement. Because the attacker can include not just 4 images, but 100 images. And the attacker can send not just 1 spoofed response, but 100 spoofed responses with 100 different IDs. And so there'll be 100 lookups with 100 different IDs and 100 spoofed responses with 100 IDs. And if there's any match between any of the lookups and any of the spoofed responses, then that 1 spoofed response will be accepted. And if the spoofed response is accepted, then it contains some additional information that will be cached. It contains a lie for what the IP address for www.google.com is. This was kind of heavy. So I'm going to walk through an example. The victim starts to load the first image on the attacker's website. To do that, has to make a DNS lookup for fake1.google.com. This request is going to go through the whole recursive process and lead to a request to the name server for Google for this IP address with some ID. The attacker, meanwhile, is sending a spoofed response. So the legitimate name server will respond a response saying, sorry, that domain name doesn't exist. But the attacker is also sending a spoofed response. If the attacker guesses the ID correctly and the spoofed response gets there first, then it'll be accepted by the resolver. And whatever it says will be cached. Because it looks like it's coming from the Google name server. The source IP address is the source IP address of the Google name server because it was spoofed. And all the information is about Google. And the particular information that's provided is cleverly constructed to claim that fake1.google.com doesn't exist, but you should contact this other name server for information about it. And the name server you should contact is the host name www.google.com. And additionally, helpfully tells you in advance that the IP address for www.google.com is evil IP address. And that survives all the bailiwick checking because it's a response from the Google name server, which is delegated authority from google.com. And the response is all the records are for something.google.com. So if the malicious response gets there first and has the right ID, it'll be accepted by the resolver and cached. So then the IP address of www.google.com will get cached, and that IP address that's in the cache now is chosen by Mallory, the attacker. An off-path attacker who doesn't have any ability to eavesdrop, who's just guessing the ID field. How are we doing so far? There's some intricate technical details. Yeah?
That's not.
Why fake one? Because the attacker is going to get the victim to do a lookup for fake 1 and fake 2 and fake 3 and fake 4, and that way get multiple chances of success. That's why fake 1. The other reason why fake one is if Mallory doesn't guess the ID number correctly, then Mallory's spoofed packet will be ignored. The legitimate response from Google's name server will be received. And the recursive resolver will remember that fake1.google.com doesn't exist and not make any more lookups for it. So to get another chance of success, the attacker needs to use a different hostname next time, fake2.google.com. So by using a different hostname each time, the attacker can get multiple chances of success. This is a race condition. The attacker's spoofed packet has to get there before the legitimate response from Google. And the key thing is that Mallory can send several spoofed packets with several IDs right around the same time, super fast. At the same time that the victim has sent multiple lookups for multiple different host names, each with different IDs. And if there's any match between any of the lookups IDs and any of the spoofed responses from Mallory, and Mallory wins the race condition, then they get a malicious IP address for www.google.com cached in the cache. And if they're wrong, the wrong ones don't prevent others from succeeding. So, if Mallory is right once, even once, then the wrong IP address gets cached. And let's imagine that Mallory gets the victim to make 256 lookups and sends 256 fake responses. Then what are the chances of success for Mallory? There's like 256 times 256 ways to match them up. And each way has a 1 in 65,000 chance of being right. So 256 times 256 is 65,000. So you got like 65,000 shots at a match. And each one of those is a 1 in 65,000 chance. So there's a good chance one of those is a correct match. It's like in CS161 when we did this birthday paradox thing, where if you have about square root 365 people in a room, then it's likely there's some pair that have the same birthday. It's the same thing here, except it's like you got a bunch of people in this classroom and a bunch of people in that classroom. What are the chances that someone in this classroom has the same birthday as someone in that classroom? It's a lot higher than you would think. So this way, instead of needing to make 65,000 spoofed packets, Mallory only needs to send about 256 spoofed packets, and they've got a good chance of succeeding. And if they succeed in any of those, if any of those is a match, then this bad IP address for www.google.com gets cached. And then if the victim then loads www.google.com in their browser goes to that IP address, sends all that traffic to the attacker, to Mallory. And so if it's not using HTTPS, then sends the session cookies for google.com to the attacker. The attacker can now use that session cookie to log into the victim's account. It's really bad. So this is the Kaminsky attack. Basically, we thought DNS was fine for about a decade, and then Kaminsky noticed we all missed this birthday trick. Everybody in the community for like a decade had missed the possibility of this attack. And this attack is much more feasible than anyone had realized. And so he was a consultant, and he canceled all his jobs for the summer. And he spent the entire summer calling up every maker of DNS software and every operating system saying, don't tell anyone, but you have to fix this. You're not allowed to tell anyone about this until everybody's fixed it, and arrange for everyone to fix it and keep it a secret. And everybody pushed out an update on the same day so that like this could get fixed. Because his fear was that if he went and told Microsoft and they updated Windows with a fix, then everyone who's looking at that update would figure out what the flaw was, and then they could attack all the Linux machines in the world. And so he needed to coordinate the fix. So he basically dedicated several months of his life to arranging to have this catastrophic flaw fixed. And fortunately, it got fixed before any bad guys found out about this flaw. This latent flaw that had been sitting there for a decade. Just the ID.
It's the same ID, but the request is fake 2, and then it comes back as fake 3. So
That doesn't need to match. Yeah. Yeah. The ID, the source address has to match, but that can be spoofed. The port number has to match. But at the time, people tended to use a hard-coded port number for all DNS queries. So that was easy. Everybody used port 53. Okay. So the innovation that Kaminsky had was 2 things. He had this trick so that if he got, when the guess was incorrect, it did not preclude another attempt. Previously, we thought if an attacker tried to send a spoofed packet and they got the ID wrong, then they would be the victim would be inoculated and they couldn't make any more attempts until there was the legitimate answer cache expired in another day. And then the other innovation he had was this birthday paradox trick to speed things up. And these 2 took it from probably not a big deal to oh my gosh, this is totally easy. Anyone could mount this attack. So the defenses that are used against the Kaminsky attack are randomize the ID, for sure we got to do. People started randomizing the source port because now the response will have to use the same port number. And if the attacker can't predict what source port was present in the request, then they can't be sure what port number to fill out in the response. So now there's 2 to the 32 possible values. There's 32 bits the attacker has to guess. So this attack will take a lot more messages. And then some people also add another defense. In the query, DNS is case insensitive. Capital Berkeley.edu and lowercase Berkeley.edu is the same host name. So what they started doing is when they sent a DNS request, they would randomly make each letter lowercase or uppercase, randomize the case of every letter. And then the response that came back checked to make sure the response matched the same uppercase lowercasing. And an attacker who's sending a spoofed response wouldn't know how to uppercase lowercase. So that would provide a few more bits of randomness that the attacker would have to guess. It makes it harder for an attacker to send a spoofed response. So today, with all of these defenses put in place, it's believed that the Kaminsky attack's probably pretty hard to mount because you would need to send so many messages. But it was a big shocker for the field to realize that there was this flaw that nobody had noticed for so long lurking in the core part of our infrastructure. Oh, I can't remember. Look it up, someone. It's probably around the mid-2000s maybe, or. And then there was another defense that said, hey, these additional information sections are part of the problem. Don't cache them. And that was kind of controversial because it reduces performance. And not everyone does that. So why do we care about DNS attacks? One reason is that people started using it for malicious advertising. For instance, if they could take over a DNS server, they would change the DNS entries for ad websites so that it redirects the browsing you're doing, the ads that you're getting served, are actually going to some other ad site the attacker controls, and the attacker is now making money from the ads you see. So they're stealing the ad revenue, basically, by attacking DNS. That was one of the early attacks on DNS. Ways that DNS vulnerabilities were how they were used for ill purposes. Of course, HTTPS and TLS stands against this because it provides end-to-end security. Even if the DNS sends you to the wrong site, the public key authentication will detect that. But in the days before, most people used TLS on the web. This was an effective attack. Okay, so in summary, DNS is this beautiful way of building a distributed database that enables making use of caching and existing organizational structures to like partition data and get redundancy. But it wasn't designed for security, and so it had security flaws, and even had one that was like the shocking like flaw, like in principle anyone should have been able to found, but that no one noticed for a long time. Let's stop here. That was a lot. The takeaway is basic DNS is insecure and we desperately need a break. So let's take a break and we'll have some snacks. 5-minute break.
We can do the.
All right, while y'all are getting some snacks, and feel free to come back for more. Two just administrative things. Tomorrow's an official holiday, so no discussion sections, and we're planning to cancel all the office hours tomorrow. And we're coming up on Thanksgiving. It's not too far away. And I'm planning to hold lecture that Monday. But I wanted to find out if any of you will be here in person. If there'll be any of you who will be here in person, I'm glad to do it here in person. I'll be here. But if no one's going to be in person, then I'll just do it on Zoom. But if anyone will be here in person, I'll do it both in person and Zoom as usual. So let me just take a poll. Is there anyone that Monday before Thanksgiving who will be here would come in person? Okay, great. Then I'll keep doing it the same as usual for the Monday before Thanksgiving. Join by in person or Zoom, whichever works better for you. Okay, so DNS, that was the doom and gloom. Oh my, security is bad. DNS has no security built in. Maybe TLS saves the day, but DNS itself has no protection built in. So now I want to show you about a scheme that was designed to add security to DNS, to defend against all these attacks that I've been showing you. And it's called DNSSEC. It's short for DNS security, I suppose. Okay. The first thought you might have how to defend against these attacks on DNS is don't use UDP whenever you make a connection to a resolver or a name server or whatever. Make that connection over TLS. Yeah, connect to a name server, use TLS. Seems like a reasonable approach. If we're worried about like man-in-the-middle attacks or spoofed packets, then TLS should defend against those. Yeah? And really, all we care about is integrity. There's nothing confidential in the DNS. But it's okay. No harm if there's some encryption too. We're mainly going for like the public key authentication and the message authentication codes that TLS gives us. Reasonable idea. Okay? So the idea is when your stub resolver sends a query to the recursive resolver, that'll be over a TLS connection between the stub resolver and the recursive resolver. When the recursive resolver connects the root name server, it'll make a TLS connection to the root name server. And when a response comes back, it comes back on that TLS channel between the recursive resolver and the root name server. And then when your recursive resolver makes a query to the edu name server, it'll open up a TLS connection and the response will come back over that TLS connection. So there will be 4 TLS connections in this picture happening. What do you think about this defense? I know it's hard to think. We're 2 hours into lecture. I'm so sorry. And I'm asking you to like a difficult analysis, evaluation question, critique my defense. Good, bad. What are some pluses? What are some minuses? Good. TLS, great cryptographic security. Other cryptographers have looked at it to make sure it should be secure. No more no man in the middle. Yeah. Yeah. Performance. What about performance? It is way slower. It is way slower. Where do you think that performance might be felt the most? Sorry, it was a great answer. I'm just exploring a little further. Do you have any thoughts? Yeah. Visiting a new website you've never been before will like require this DNS lookup and some TLS connections, and my page might load slower. Any other place where you think the performance might hurt? The pain might be noticeable? Yeah.
So is it TLS individual for each like hop?
Each hop, yep. Separate TLS connection for each hop.
So caching stuff already for .NET and like if we're accessing something under .NET, again, that's not like it.
We're caching, so that should help with performance. Yep, yep. Yeah? You're worried about security, and what if the recursive resolver is? Yeah, the recursive resolver is usually a server. Like right now, my machine is using some server that Berkeley set up that's running a recursive resolver. It's a different machine from my laptop. The TLS connection is between, let's say, the recursive resolver and the berkeley.edu name server. So it gets decrypted by the recursive resolver. The recursive resolver sees the answer and can cache it. And then there's another TLS connection between the stub resolver and the recursive resolver. So it's like it gets re-encrypted to send to my machine and then decrypted by my machine. There's a lot of handshakes. Yeah. These DNS servers, the load on these DNS servers is going to become a lot more expensive because each request is not just a packet that it sends a response to, but now it has to do a Diffie-Hellman public key exchange as part of its TLS connection setup. So I think servers might get very overloaded trying to handle all of these TLS connections. So it could slow down page loads and it could overload DNS servers. So performance is a big, big problem here with this design. Another problem with it from a security perspective is that it doesn't defend against malicious name servers or malicious recursive resolvers. Maybe it's easiest to explain the malicious recursive resolver. If I'm using a recursive resolver and that recursive resolver is actually malicious or misconfigured or hacked, it can lie to me about what the results of the lookup are, and I will never know. Even though I have a TLS connection to it, prevents any man in the middle, it doesn't prevent lies. I'm trusting whatever the recursive resolver sends me. And if a name server lies about host names within its zone, it doesn't protect against that either, right? So this might sound like a little bit obscure threats, but there are some security risks still remaining. So it's kind of not ideal, both because the performance cost is really high. This kind of is like really expensive and painful, but also because security-wise, maybe there's opportunity to do better. It's pretty good. It's pretty good. But there's a little bit of remaining risk. And the reason is that there's a mismatch between what TLS provides and what we really want from secure DNS. TLS provides a secure communications channel. And if you want a secure communications channel, TLS is your person. It's perfect. It's wonderful. But for DNS, that's kind of not what we want. It's not so much about the communications channel over which what server we're talking, that like between me and the server that I'm talking to, but it's like the data that I received. I want to know that the data that I received is authentic. This DNS record that I received is authentic. And that's sort of a little bit different. Like, how did that DNS record get to me? I might be getting it directly from an authoritative name server by a TLS connection, but I might not. I might be getting it from some cache that got it from authoritative name server, or there might be multiple levels of indirection happening there. However I got it, I wanted to be protected that whole pathway from the name server to the cache, and then while it was stored in the cache, and then while it's between the cache and me, I want to protect, ideally, I'd like to prevent against an attacker messing with things at any of those steps along the way. So this is what I mean by this like object security. This is not a standard name, but I'm trying to come up with a name for something that distinguishes from securing a communications channel, securing a TCP connection. And TLS provides channel security, but we really want this security for this piece of data throughout its entire lifetime. So that's what DNSSEC does. DNSSEC provides this stronger notion of security. Now, DNS over TLS is used. It's been enabled. It's used, I think, by Firefox. It's not perfect. For backwards compatibility, not every DNS server supports TLS, and not every browser supports it. So what Firefox does is it tries connecting over TLS, but if it can't, then it falls back to the ordinary unencrypted, unsecured DNS. And so that means that like a man in the middle attacker can perform a downgrade attack where when Firefox tries to make a TLS connection, the man-in-the-middle attacker like blocks that connection, spoofs a reset packet or something, so that the machine will fall back to using unencrypted DNS. So it's not perfect, but it's partial progress that is easy to deploy. So it's kind of like interesting to see that this idea is used, even though it has some trade-offs. But I want to show you DNSSEC, which provides a stronger level of security and better performance also. Okay, so DNSSEC is basically an add-on, backwards compatible add-on to DNS to provide this level of security that we want. And I want us to design it together. So I'm going to give you some challenges to think about how you might do this. First question, what kind of cryptographic building block? We've seen a bunch of cryptographic building blocks. What one do you think might be best suited to the goals we're trying to achieve here? Like run through in your head all the cryptographic building blocks we know of. Just some like first off the cuff guess. What are you thinking?
Some digital signatures.
Max and digital signatures, because it's like integrity we care about, not confidentiality. Okay, good. Max or digital signatures, I like it. That seems good to focus on maybe either Max or digital signatures. Any thoughts about how to choose between those two? Asymmetric versus symmetric, yeah?
I am to say that, like, you know, because we're not doing any encryption, like having public key to throw around is probably easy to set without having to like hide it.
Max, I have to like distribute MAC keys, whereas signatures feels easier to do the key
Like,
distribution.
Like find some keys that like an outsider can't read what it is.
Yeah. What do you think?
Yeah, I was thinking so. DNS record.
DNS records should be public, so public keys are sort of like consistent with that. Yeah. 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 Okay, so digital signatures then, rather than Max. One thing that's very nice about digital signatures is that they're cacheable. They work really well with caches. Like, same thing with certificates. Certificates are kind of cacheable. I can get a certificate from anyone, not just the certificate authority, and still validate it. And DNS relies so heavily on caching that digital signatures sound really attractive. Okay, so let's use digital signatures. We want everyone to be able to verify that these records are valid. Not just like one person who knows the MAC key. If we use Max, we'll have to figure out how to get a MAC key to the right person, and sounds like a headache. Okay, so we're going to use digital signatures, which means that presumably we should sign every DNS record. Every DNS record will be digitally signed. When you get a record, what are you going to need to do to make sure that it's authentic and hasn't been tampered with? What's that? Verify the signature. Verify the signature. Okay, so the recipient will have to verify the signature. So presumably whichever like name server created that record or is authoritative for that record should sign it with its private key. And then the resolver, when it receives that, should verify the signature using the name server's public key. Okay, I think we're starting to get a design here. Nice thing is that everyone will be able to verify that record truly came from the authoritative name server. So like the idea is if the recursive resolver asks the Berkeley name server, what's the IP address of each Berkeley EDU, then the Berkeley name server should respond with what? What should be included in the response? multiple things. I'm looking for you to suggest some of the things that maybe should be in a response. Yeah? The IP address for East Berkeley EDU. Yeah. So the IP address or that DNS record, which will include the IP address. Digital signature over the record, signed with the name server's private key. And maybe we might include the name server's public key so that you can verify with that public key. Maybe. We could talk about that. Sign with the private key. Verify with the public key. Okay. Okay. So we got the beginnings of a design. Yeah?
Like, you break it, but you can just make your own little private key, sign it with that, and provide your own public key.
Yeah. How do we know? How does the recipient know whether that's the right public key of the legitimate servers, not just as opposed to the attacker's public key, you know, in a spoofed response? So there is some ambiguity here. The recursive resolver can't just accept whatever public key it receives. It's going to have to have a way to check that that's a valid public key. How should the recursive resolver check that that's the right public key?
Reading method.
You're reading ahead to try to figure out. Okay, all right, yeah. Any thoughts on options?
Well, I think we have one that we've seen before.
What's that? Certificate authority. So we could have a certificate authority that keeps track of the public key of every name server. Absolutely, we could totally do that. But DNSSEC doesn't do that. DNSSEC doesn't do that because that would require an additional like certificate authority, and DNSSEC is like, no, I just want to use the existing DNS system, and it has a clever way to basically have the DNS system be its own certificate authority. Because see, like DNS already has this notion of like which name server is authoritative for each zone, which is starting to sound a little bit like a certificate authority.
Instead of trusting, it's kind of the opposite. Instead of having like big servers that that like know everyone, we instead trust, I guess, like our router who would like tell us, oh well, we need to go to here, and this is their like public.
Yeah, in a certificate authority, like for the web, there's one entity who knows like everybody and issues certificates for everybody. But DNS is not like that. It's partitioned, right? DNS is like has these referrals and delegation of authority and a tree-like structure. So DNSSEC is going to try to mimic that. So it's going to try to do something like certificate authorities. This is a good idea. Certificates are a great idea, but we don't want to use like a separate certificate authority. So there's a little piece that's missing that we're going to need. You have to make sure that nobody's tampered with the public key, that we have the right public key. Where do we get the public key from? Yeah. Did you have a question or a comment? Oh, I thought you raised your hand. Yeah. Use the root servers as the root of trust. So should the root server know the public key for every name server? The public keys of all the name servers are next level down. So the root should know the public key for the .com name server and the .edu name server. Who knows the public key for the berkeley.edu name server? The .edu name server knows the public key for the berkeley.edu name server. Yeah. So DNS already has this delegation notion where you find out which name server is responsible for a zone. When the .edu name server tells you which name server is responsible for berkeley.edu, it should also tell you the public key of that name server. The way it should identify the name server that is responsible for berkeley.edu is not by a host name, but by a public key. Because public keys are cryptographically secure. So we're actually going to bake this certificate or certificate issuance into the DNS. So how does a name server delegate trust to a child name server? The answer is the same way we do certificate chaining. The parent name server is going to provide a delegation and sign the public key of the child name server. And all certificate chains, all kind of hierarchical certificate structures need a root of trust. Who's going to be the root of trust in DNSSEC? Sorry, say it a little louder. Yeah. Yeah, the root name server, the root of the tree is going to be like our trust anchor, our root of trust. Okay, so if the recursive resolver asks the root name server for the IP address of East Berkeley EDU, it's going to say, I don't know, and then respond with a delegation. Say, I don't know, but talk to the name server for .edu. Here's the name server that is authoritative for all names that end in .edu. In plain DNS, we would identify that name server, the .edu name server, by providing the host name of it. But in DNSSEC, we also provide the public key of the .edu name server. And then because all records are signed, all records that the root name server responds with are signed by the name server, that statement will be signed by the root name server. So the response will include a statement. This public key is the public key of the name server responsible for .edu, signed by root name server. And that is exactly a certificate. A signed DNS record that has a public key in it is a certificate. So this recursive resolving will give, at each step, give the public key of the next server to contact, which is everything you need to verify the signatures on the responses when you contact them. Okay, so in detail, DNSSEC, all records are signed with a digital signature. So this is going to defend against on-path attackers and in-the-middle attackers. When you cache a record, you can cache the signature with it. You store both the record, the signed record, you store both the record and the signature, so that if someone else, like a stub resolver, asks you for that cached entry, you can return the record and the signature, and they can verify the signature. So signing works very well with caching. Name servers are in this tree structure. Parents delegate trust to children, and we represent that by these signed delegations. Signed certificates, basically. So now malicious name server, this limits the damage that a malicious name server can do. If I register the domain name davewagner.com, I can serve as I can set up a name server that's authoritative for all names that end in davewagner.com and get signatures from the .com name server for my name server's identity. But that delegation will only provide authority to my name server to respond to queries about something.davewagner.com. And I don't have the private keys that would be needed to create signed records for google.com or amazon.com. Only Google and Amazon have those private keys. When when I set up a name server, the name server generates its own private key, public key pair. If I register a domain, I buy a .com domain name. Then I go to the entity that's responsible for the .com name server and say, I want to buy this domain name. And they say, sure, no one else has that. It's yours now. And they say, tell me what name server to direct people to if they want to know about names under your domain name. And I tell them the host name of my name server, and I upload the public key of my name server too.
So, but like, why do you still like in like the previous slide, it says like, there's the public key of my child and there's my own.
Yeah.
I don't get the second part, right?
Yeah, in practice, actually, each name server doesn't need to send its own public key because the resolver should already know it from the parent. You're right. It was a little bit of a lie. Each name server doesn't need to respond with its own public key. Yes. Totally correct. 100% right.
Like points to trust only from like if you get it from
Only if you get it from the parent. That's right. Only trusted if you get it from the parent. Yes, that's correct. Yes.
For the next 4 days, I'm still the owner of Berkeley Physics, but I bought this domain from GoDaddy. Is there sort of like GoDaddy like taking care of all this stuff in the background for me? And if so, can I like mess around with that stuff?
Yeah, so like GoDaddy, you can think of them as controlling the .com name server. It's not quite right, but let's start with that as the basics. Think of them as controlling the .com name server. So when you buy a domain from GoDaddy, they're like, okay, no one else has that domain name. You give them $20 and they're like, it's yours now for the next year. The simplest way to think about it is that you tell them what name server to send people to for your domain name. And they'll add that as a delegation to the .com domain name, and that's it. They added that one record into their like database, and they're done. They took your $20 and they promised to respond with that one record for the next year. Now, in practice, a lot of people who buy a domain aren't necessarily technically sophisticated enough to run their own domain name server, right? So GoDaddy also has a service where they say, if you don't want to provide your own name server, we'll run a name server for you for your domain. Just tell us, we'll use our own name server, and you can enter in whatever records you want. So that's an alternative way. And then the authoritative name server for your domain, berkeleyphysics.com, is not your name server. It's, ns17.godaddy.com. And there's some database there. And then there's a website on GoDaddy where you can say, hey, change some of the entries in that database for mail.berkeleyphysics.com, and they'll manage that name server for you as a service. So it's kind of bundled together.
How, like, because it's very easy to see, oh, Google has access to like mail.google or something.google.
Yeah.
How does somebody know that GoDaddy has access, or is it authoritative?
To simplify your life, imagine that GoDaddy is the only domain registrar for .com. It's not actually real life. In real life, there's like multiple domain registrars for .com. So there is one company, I think it's ICANN, who says we're the coordinating authority, and there's multiple companies who can sell .com domain names, and we'll help coordinate amongst them to make sure that there's no conflicts between them. I don't know the details, some crazy way of allowing to have multiple companies. But that's sort of beyond the scope of DNS. I don't know if I answered your question. Ish. All right, so when you do a DNS lookup, the recursive resolver, which does all this stuff for us, starts by asking the root name server, gets back a response, I don't know, and a delegation to the .edu name server, which includes both the host name of the .edu name server and the public key of the .edu name server. So then your recursive resolver tries again, asks the same question now of the .edu name server, gets back a response, Remember that all responses are signed. Recursive resolver now knows the .edu name server's public key so it can verify the signature on this response. In this case, the response will be an I don't know, let me like refer you to the Berkeley name server. And here's the public key for the Berkeley name server. So the recursive resolver will try again, contacting the Berkeley name server. By now, my recursive resolver knows the public key for the Berkeley name server. So when it gets a response, it can verify the signature on that. And in this case, the response will be the IP address of xberkeley.edu. So by going through this whole process and checking the signatures at every step, we have learned that the Berkeley name server is authoritative for every name that ends with berkeley.edu, and it tells us the answer. And so now we have an answer that we can trust. Okay, so DNS implements this by adding some new record types. In addition to the A and the NS records for addresses and the name servers, there's also a signature record. There's a DS record for like delegation and an RSIG record. And basically between them, they have the signature. So the signature is actually not, it's sort of like, you don't have to modify the protocol. It's just an additional record that gets returned in the response. So this makes it backwards compatible with DNS. So when you send a query, the response comes back with like an A record or an NS record, and then also these additional records, DS and RRSIG, that have the signatures on the other records. So every response has some normal DNS responses and then some DS and RRSIG records that have the signatures on them. Whew. Any questions so far? Why does it include the hash of the child's public key instead of sending the child's public key? Totally could just send the child's public key. I don't know why they did it this way. Either way would be fine. Okay, so I don't care that you know all the little intricate details of DNSSEC, but I thought it's more an interesting case study where you figure out what the security needs are, and then you match up the cryptographic primitives to what the security needs are. If you need channel security, you need to protect a connection, you use TLS. But if you need to protect data that has some kind of longer lifetime that flows through a system and is cached here and served there and sent over multiple channels, and then instead maybe you have a different kind of security mechanism like digital signatures or public key encryption. And I thought it was a really nice example of how you could integrate the cryptography together with like the caching that DNS relies on to be high performance. So that's the main thing I wanted you to see. And then I have a little intricate details that maybe are nifty for those who like to get into like dive into some technical details of like some clever stuff. Maybe now would be a good time to take like a 2-minute break before we like dive into anything more. Let's take a stretch break. All right, so now I'm just going to show you some little details that you are totally not, by far, not the most important thing I'm going to show you today. If you went home now and you understood everything up till now and didn't understand a single thing after this, I would be so delighted and thrilled. So this is like, oh, if you want to see some cool add-ons and stuff, I'll show you some cool add-ons. I suppose it could be. It's not my highest priority. So like if you're lost about the stuff that I was showing you so far, like conceptually the basic idea, I definitely want you to tell me so I can like help you with that. That's more important. So you can totally like stop me. I don't mind if you're lost. You're not like wasting people's time. You think you're just lost. You want to keep going? I don't know about that. You might not be. How many people are lost?
Okay, then it might just be.
Ish. Anything you want to you want to say about the parts that are confusing that I could help you with, or? And I'm putting you on the spot. I'm sorry. It's totally not fair. I just wanted a poll, and then I asked for more.
If I understand it.
Yeah. It's hard to like separate out like the main idea from all the little details that are floating around here. Yeah.
Instead of just directly giving the IP address of like which network.
Yeah, isn't that kind of whacked? Why does DNS give you the host name of the name server rather than directly the IP address? I really have no idea why.
But are you guaranteed to always have the IP address in the domain name? Like, otherwise, like how will you get that IP address of the child host name?
Yeah, if all you get is the domain name of the name server you're being referred to, how do you get the IP address? I think you have to do another DNS lookup. Then I think there's a risk that you could get into an infinite loop. So I don't know if you're guaranteed to always have that additional information that also provides the IP address. Maybe it's guaranteed, maybe it's not. I don't know, it's a weird design. I really don't understand why they did it that way. Probably someone like thought about it really hard and had some good reason, but
But why they didn't just directly give you the address of the.
yeah.
How can you cache it? Let's say the authority changes, and the IP changes. Which you can, right? Especially if you go to a different location or something.
Okay. Could be that maybe when it was designed, the designers were thinking that it's rare to change the host name of the name server that's responsible for a zone, but it might be common for its IP address of that server to change. If that was what they were thinking, then the current design would make sense to me because it separates out those two issues. I don't know if that's actually true today. I suspect that it's rare for those host names or IP addresses to change today, but maybe. I mean, also a lot of systems on the internet were designed before they got big, and people were making a guess about how they'd be used, and then some of their guesses might have been wrong. So today we might design them different. Yeah, it's weird. When I see the design, I wonder the same thing too. Yeah. So I guess the two core ideas of the DNSSEC are sign all the things, sign everything. Every record gets signed. Signed records are awesome because you can cache the record and the signature. And then you can give the record and the signature to someone else, and they can also verify the signature. So that's like number one idea. And then I think number two idea is certificates. But don't use the certificate authority like on the web. We're going to reuse the whole delegation notion that DNS has to use the same certificate structure for DNSSEC as DNS has for delegation. I think those are the two main ideas. And then the rest is just finding a way to shove it into the packet formats and record types and so on. Yeah, I guess only the resolvers do that. But you can actually have caching name servers. You can actually speed up a name server by putting a cache in front of your name server. So when people go to the authoritative name server, it's going to some cache, and then there's a backend thing that, yeah, you can put caches at various points in here.
Like you're just the client. There's no point for you to cache a big this. So
Yeah, if you're just a client, it's great to cache everything. Well, you might not need to cache the digital signatures. That's true. If you're just a client, the stub resolver doesn't need to cache signatures, just the records. Yeah, that's true. Once you verify the signature and then you can throw it away. Okay, good point. Yes. The recursive resolver, though, should cache the record and the signature so it can provide both to the stub resolver. Yeah.
Sorry, I was not like. They are, that's it. Right.
Yeah.
You verify that it's from the record by just verifying it. Like.
If you got the signature, you've got a record from
Something claiming to be the record. You
Yeah.
just know it is record because verified.
How do I know? How do I verify signature on things claiming to be from the root directory? DNSSEC clients have the public keys of the root name servers hard-coded in the code. The same way as your web browser has the public keys of certificate authorities hard-coded in the code. Everything has to start somewhere.
Yeah.
Something has to get us started. Yeah. Okay. Now there's a couple other tricks in DNSSEC that are kind of cool that maybe just are fun to look at for the people who love data structures and stuff. Here's a cute idea in DNSSEC. DNSSEC works great for domains that exist because there's a record for each domain that exists. What about when someone makes a query for a host name that doesn't exist? Query a host name and the response is there is no such host name. What should we do? What should DNSSEC do about that? One option is don't authenticate the responses that say there is no such domain. Don't sign them, don't authenticate them, no protection. That is plausible, will have great performance, has possibly a mild security risk, which is that anyone can spoof those responses. So if I look up Amazon.com, I might not get the valid response and I might get a spoofed response saying, I'm sorry, Amazon.com doesn't exist. And that would be like a denial of service attack. Not a big deal, but you could imagine some scenarios where it might not be ideal. Like, I don't know, I'm trying to contact the police hotline or the New York Times whistleblower tip page or something like that, or visit some, resource that my government doesn't want me to see. And an on-path attacker is censoring those DNS lookups and replacing them with sorry, there is no such host name. Those kinds of attacks would be possible if we don't authenticate the responses that say, sorry, there's no such domain. The other option would be to sign the responses that say, sorry, there is no host by that name. That domain name doesn't exist. You could have the name server sign those responses. But that's has some trade-offs too, because that can't be cached. You can't anticipate in advance all the non-existent host names that someone might ever ask. So the name server will have to have a private key stored like online, like in its hard drive disk, so that it can sign its response saying, I'm sorry, that crazy host name you asked about doesn't exist. So if the name server gets hacked, then that private key gets compromised and people can spoof domain names. Whereas the positive responses for host names that do exist, the signatures can be pre-computed and don't need to be stored accessible in hot storage on the name server. It's kind of like if you're familiar with like Bitcoin hot wallets versus cold wallets. So there is but the secure answer is to say sign these responses, but that has a slight trade-off, which is the name servers now, if they get hacked, it's a higher severity situation. They have to have the private key available for real-time signing. And also there's a performance issue that signing is slow. So it could slow down name servers if they're signing every negative response. Yeah. What's that?
Oh, I guess that's, but like, if someone performs like a request for Google.com, right?
Yeah.
And you transfer them over to something, right? And
Yeah.
you get their response, you still have to sign the response. Like, if you want to cache that response, you would have to re-sign it, right? So don't you have to keep your
Responses can be pre-computed and like stored for a while.
Yeah, but at least in the first database, doesn't every like name server also have cache? On like what other like maybe like .edu has like, I don't know, does .edu would it have like classes.berkeley.edu?
Usually not.
Not. So
Usually it would just be one level referrals. Yeah. No. So maybe neither of these are that big a deal, but if you're a security purist, you're like, oh, I don't like either of these options. Neither one's fully satisfying. And so people came up with a clever trick that's better than either of these, even though either of these would probably be okay, probably be fine, not a big deal. And what they have, this is an extension called DNSSEC, which allows authenticating a negative response, but in a way that does not require the name server to sign things on the fly or have its private key stored accessible on that name server machine. It's a cool trick. And the trick is the name server sorts all of the host names within that zone. Okay, so if this is the Google name server for google.com, it might have maps.google.com and one.google.com and web.google.com. It just has a sorted list of all of those names under google.com. And then it pre-computes, looks at each pair of adjacent records in this sorted list and pre-computes a signature over each pair. Has a signed statement saying there is no host name before maps, and another signed statement that says there is no host name between maps and one, and another one saying there's no host name between one and web, and another one saying there is no host name after web. And then if someone looks up non-existent.google.com, the Google name server can look where that would fall in this sorted list. Aha, it would fall between maps and one. It doesn't actually exist. And return this pre-computed, pre-signed response that says there is no host name between maps.google.com and one.google.com in alphabetical sorted order. And that is enough for the resolver to verify that this domain name doesn't exist, because it would, in sorted order, would be between after maps and before one. Does that make sense? It's like really clever data structure, especially a linked list. And you sign each like pair of nodes in the linked list. But then security people are such critics. Nothing's good enough for us. Then some security people saw this and they said, well, I don't really like that it makes it super easy to find out what are all the host names under google.com. I don't know whether this actually should be treated as confidential, but some companies were like, well, sometimes when we have some secret project that we haven't announced to the world, we'll create some host name based on the name of that secret project. And so I don't want anyone to be able to like identify all of the host names of all of the machines under my zone. And this structure makes it easy because someone can start by like doing a lookup for AAAA, get a response that says there is no host name before apps, and then query right up, AQ and get a response. There is no host name between apps and map, and in sort of linear time, find each of these, walk down this linked list, find each of these pairs, enumerate the list of all of the host names in that zone. And then people on the committee started to debate, is this actually a problem or not a problem? Some people said, come on, no big deal. There's nothing secret about the DNS. And some other people said, well, I don't like it. It's not true of the plain DNS. You're making things worse for me. And so it's kind of this like awkward situation where it's not clear whether I should consider this a security bug or information leakage, but maybe. So everybody kind of like argued with each other and couldn't agree and went home and they're like, I'm not sure what to do. So then they came back the next year and some cryptographers said, okay, I'm tired of arguing over this. I'm going to propose NSEC 3, which is like NSEC but better. We're going to try to solve this problem of domain enumeration, even though I'm not sure if it's a problem. Let's just accept that some people don't like it and try to get rid of it. And so their idea is instead of having a list of the names, we take each host name in the zone and we hash them. And then we sort the hashes. And now we do the same thing on the hashes. For each pair of adjacent hashes in the sorted list, we sign a statement that there's no other hash in between these two. So maybe maps hashes to C612F3, and maybe Android hashes to D810DE. Why replace the names with their hashes? The idea was it's not so easy to go back from the hash to the name.
I see. Oh, so you can't figure out the.
So you can enumerate the hashes of all the domain names, but not so easy, maybe, to go back to the names themselves. So if someone's choosing a host name based on their like secret project, I don't know, Windows 14 for Mac, Windows 14 for ARM, .microsoft.com. We didn't just reveal to the world that, oh my gosh, Microsoft has a secret project to build Windows 14 for ARM. Okay, clever trick. Clever trick. You got to admire the cryptographers for trying to like address the complaint. So now it makes it harder to enumerate names in the zone. And what I like about it is that everything here is still cacheable. All these, like, there is nothing between these two hashes can be signed, and that signed statement can be cached. And it doesn't require the private key to be online on the name server, can be pre-computed. When the host names change, okay, you have to sign and update, but that can be on a machine that is kept offline, not connected to the internet, so maybe more secure. But it's not really perfect because people who choose short domain names, it may still be possible to reverse from a hash back to a domain name by doing like dictionary search, brute force search over all possible, short words or short names and hash all of them and see if any of them match. So cryptographers are still working on this and they have a new proposal. NSEC 3 wasn't good enough. They have an NSEC 5. Why? I'm not sure any of this is important. I'm not sure any of this is needed, but sometimes security people end up going down this deep rabbit hole of like, if there's anything wrong with this, I get really worried that maybe it could be all terrible. So I don't know. I'm not sure it's a good use of time. All right. In practice, knowing that DNSSEC is not that widely used. Here's the wah wah. We designed this incredibly beautiful, sophisticated, clever, efficient solution to the problem. And it's used by, I think, like less than 1% of DNS zones on the internet. It's been around for like 10 or 15 years, and it's still not very widely used. And why not? Largely because it's an extra operational headache to configure this and maintain it and update it. And then on top of that, you have to be backwards compatible with all the machines that don't understand DNSSEC. So real machines are configured, if they support DNSSEC, to first try doing a DNSSEC lookup. And if that fails, go fall back to an ordinary DNS lookup, which means that if there was a man in the middle, they could block the DNSSEC lookup and then attack the ordinary DNS lookup. So how much security did we get in exchange for this hassle? It's sort of debatable. And then on top of that, the widespread use of TLS has largely made this not a big deal in practice. And so people tend not to feel a large of pain. There's an administrative headache, and there's challenges of incremental deployment given backwards compatibility. And so the end result is attempts to try to get everyone to use DNSSEC have not been super successful so far. So we have this beautiful solution that's mostly not used, but I wanted to show you the solution because I think it's a really nice worked example of how you can add security to a system and how cryptography is not just channel security. You can take into account the entire lifetime of your data and end up with stronger security solutions. All right, that's all I've got for today. Thanks so much for spending 3 hours with me on DNS. Have a great week.